today we're going to have a look at this, what should be a sort of an oscilloscope style digital multimeter. This will be the Tooltop ET828 Pro. We'll have a look at that in a minute. I was so captivated by this meter, I went out and I purchased this meter with my own funds in order to be able to do an assessment of it. If you found this video to be informative, please give it a thumbs up, or better yet, subscribe to my channel. Also, I appreciate questions and comments. It really helps me know where I can focus my efforts. Now let's get into the box. So I ordered this from China, AliExpress. Came pretty quickly. Okay, very snug fit in the envelope. And so there we have it. It's called a 2-in-1 multimeter oscilloscope. It says it's a, wow, that's a mouthful, professional waveform multimeter. So this is a newer model. This is the 828, or it should be the 828 Pro. Yeah, Tooltop 828 Pro. I spent quite a lot of time trying to find out who the original manufacturer is. I don't know if it's Tooltop or someone else. So there's a set of probes here. And the probes are fairly stiff PVC. And there are some safety shrouds on the probe tips. They're pretty sharp. We'll just leave those shrouds off. So there's nothing else in the box. There's well, aside from the manual here, there's a simple operation diagram. So that's useful, kind of quick started guide. And then there's a user's guide. And this whole user's guide is in English, and it's about 30 pages, 31 pages long. So there's a lot to this unit. Okay, now let's put that to the side for a second. And it's nice that they've provided a pouch. And inside, there it is, Tooltop ET828 Pro. Now, it's an incredibly light unit. And I have to admit, I'm tempted to do a teardown of this because I'd like to try to find out who the OEM is for this unit. So stay tuned for the teardown. I'll try to do that at the end. Now, I don't know if you can see here, but they've tried to give us a little bit of guidance about what order to install the batteries in order to, I guess, make life a little bit easier to get them in. So we're supposed to do the ones on the outer edge first, and then the center one. And once we get the batteries in, it's clear why we had to do that, because the batteries kind of go a little bit under a lip of the plastic here. Let's just put that door back on. Okay. And so now we're ready to power this up for the first time. Well, how do we turn it on? Oh, that's obvious, isn't it? Oh, system turn on. Okay. Well, I'll tell you right off the bat, that dial is really stiff. Really stiff. Of course, it's interesting, we can turn it off at the other end. And so now we'll put it through some paces. Starting with DC voltage, we've got a reference supply, and I'll be calling out the reference points, but the actual high resolution values will appear in the overlay. So let's turn this on. So at the beginning, so this is 10 volts. This is 7.5 volts. This is 5 volts. And 2.5 volts. So pretty close to the identified reference points, but a little further off if we were to take into account the actual measured reference values. Now for AC voltage, since I don't have a reference source, we're going to compare the ET828 Pro to the BM79. You can see right now a little bit of ghost voltage. I'm now going to turn the power on. And you can see that they both read pretty close to the same value. The Bryman sort of wiggles a little bit in that last digit. And of course not as much variance on the Tooltop since it doesn't have the same level of precision. We'll do that one more time. And you can see the performance on the Tooltop in terms of locking into the voltage is pretty good, pretty comparable to the Bryman. Now looking at resistance, I'll be calling out the values, but the exact values are in the overlay, and I'm using the probes that came with the unit. So now let's get started. This is 10 ohms, 100 ohms, 1000 ohms, 10K ohms, and 100K ohms. So pretty good, pretty close to the reference amounts, and pretty good performance. Now capacitance, I'll be calling these out, but the references are in the overlay as before. So this is 100 picofarads. This is 1 nanofarad, 10 nanofarads, 100 nanofarads, 1000 nanofarads, and 10 microfarads. So the performance on capacitance is pretty good. The accuracy you'll have to review based on the overlay, but the performance is quite good. Now looking at diode check, I've got this checker box to just see how the reactions are. So put that there. That looks about right. That looks about right. That diode lights up. That diode lights up. That's about right. That's about right. That one lights up. And that one lights up as well. So, and then the short circuit. So good indication of the voltage and reasonable readout on the forward bias voltages, but you'll notice that there are no sounds that come out of the unit as we're doing this. And one of the things that I'm generally looking for with diode checks are multimeters that provide a little bit of a short beep when a reasonable forward bias voltage is present. So that's on these two top ones, and a continuity beep when it's a short circuit, because that helps avoid having to look at the display all the time when going through a lot of test points on troubleshooting a board. Now for continuity, I tap the probes together and see if it just can pick things up. I've switched to using a pair of gold-plated probes because I found that the probes that are nickel-plated that come with these units tend to interfere with the continuity test, and that the continuity operation is usually much better with these gold-plated probes. So in fairness to the unit, I've switched the probes. So okay, well, that's excellent performance on the continuity. Very, very good. Very, very good. For DC current, we've got a little circuit here. It's got a 5-volt input. There's a 150 ohm resistor. We can use Ohm's law, and we can calculate out that we should get about 33 milliamps out of this. 33 milliamps is 0.033 amps. Right now, we're set up into the amp range, but after doing amps, we'll switch over into milliamps. So let's turn this on. And pretty quickly, it comes in at 31 milliamps. We'll wiggle the cords a little bit. 30 milliamps. Okay, 32 milliamps. So maybe a little bit of resistance, poor contact somewhere. 32 milliamps is what I typically see with this. Now let's just turn this off for a second. We'll switch the probe over here into the milliamp range, and we'll dial this into the milliamp range. We'll turn this on, and you can see that we're measuring around 31.5 milliamps. So with milliamp range, we can get a little bit more precision on what we're seeing out of this circuit. So that's pretty good overall. Very consistent with what I've seen with most other meters. So that's generally very good. A couple of features that I haven't really talked too much, with the meter. The meter does have sort of a relative mode, which can be used to zero out the probes. pH is peak hold. The select button is used when you're trying to select between features that have different settings. For example, right now, this is in the DC, millivolt range. But if I wanted to change to AC, I would press cell, and that changes to the AC voltage mode. And so that's what cell is for. RNG is for choosing the range if we wanted to sort of do some manual ranging. But one of the things this meter has that is not at all obvious on the surface of it is it has the ability to store readings. Now, the storage of readings is a little bit awkward. So let me just show you how that works. So when we're sort of sensing a value here and we want to store a reading, we press the S key, which is kind of a hold or a stop mode. So if I press S, you see the stop. This one still is active, showing the actual value, but this one is frozen. Now, when we want to store that, we need to, in this stop view, we need to press the S key down for 2 seconds. And that takes us into what it calls, and I hope you can read that, the DMM database. And you can see I've stored a couple of values here. So it turns out that there's 100 slots for storing readings. And so then I can move to a slot. So I'll just move down here to reading 5. And then I can say save. And so you can see now it's saved the reading that I had on the other screen, AC 254.1 millivolts. And so it's stored that reading into that slot. And when I want to get out of this mode, once again, I hold the S key down for 2 seconds, and I'm back to the mode that I was in. The thing that is a little bit troublesome to me about how this works is that it's fairly tedious. If you wanted to store several values, you'd have to go through. So let's say we wanted to store another value here. It'll probably be the same given the... So once again, I press S to stop the reading. I hold S down for 2 seconds to go into the storage view. I move to an empty slot. I press save, and then I've saved it. So I can save these things, and I can save these things in these various slots, but that would mean I also have to keep track of which slot I've saved certain readings in. So maybe there's some sort of logic that I might apply, the first 4 readings or something like that. Who knows what I might do. The thing that's a little bit odd is there's 100 slots like this. So you can see this shows 0 to 9, but there's also 10 to 19. And going through these pages, I can't go backwards. I can only go forwards, either forward across the pages, or I can go down through the slots, and then it loops around. So maybe that's handy, maybe not. I can certainly see the utility of being able to save readings and store those. That's really great. Except the usability of this feature, I'd say it leaves a little bit to be desired. Now, this multimeter also has an oscilloscope mode. That's why it's called a graphical multimeter. So let's start it off. I've got it hooked up to a function generator here. So this function generator is currently putting out a 50 kilohertz sine wave. You can maybe make out the information on the display panel of the function generator. And we're going to turn the Tooltop on. And initially, we're at 10 milliseconds per division. And it's kind of very coarse. So let's see if we can zoom in a little bit, so to speak. So we'll press the F1 button, which corresponds to time here on the display. And that's 10 milliseconds per division, 5 milliseconds, 2 milliseconds, 1 millisecond, 500 microseconds, 200 microseconds, 100, 50, 20. We'll go one more. So that's 10 microseconds per division. And so we see the grid there. And down here at the bottom, perhaps you can see that it's calculated the sine wave at 50 kilohertz. So that matches what the function generator is putting out. So that's how we change the time per division. We can also change the volts per division over here. So that's with F2. And so, of course, we can make that, we can increase the volts per division, we can decrease the volts per division, but we'll leave it there. That's a good range here. We can also change the backlight brightness. It's a little brighter, a little dimmer. Let's leave it brighter. It should help with the video. And then we can also change the trigger, although I'm not going to go and through the full activity of testing out the trigger, but we can change the trigger mode from being either a rising mode to a falling mode. And so it'll take either a rising trigger or a level falling trigger. Now, so that shows a sine wave. Now I'm going to start going through different kinds of waveforms in the function generator. So let's pay attention both to display over here, which will give an approximation of what the wave looks like, and the display here on the Tooltop. So press wave. So now that's a square wave. And you can see on the Tooltop there are these little kind of like flickers here. I also tried this out with the function generator out with a more powerful oscilloscope, and we don't see all of these little spikes that appear. So we can tell that it's a square wave, but a little bit odd with the little kind of spiky noise that appears. That's more a function of the Tooltop than it is a function of the signal generator. So that's a square wave. This is a rectangular wave, not much different there. This is a trapezoidal wave. In this case, not much different. Let's see. This is a form of pulses. Here's a trigger test. And then this is a ramp up. This is a negative ramp. This is a staircase trigger. And what you can't really tell so well is that these are really, let's see if we increase the voltage per division here. These are broken up into more specific levels, and so it's not as continuous in terms of the staircase as is suggested here. A stair step wave, and every once in a while you see that this kind of dropping down here, so that's sort of noise in the operation of the meter. Here's a negative stair. This is a positive exponent. This is a negative exponent. And once again, you can see this sort of sensing noise that's more a product of the meter. on my Regal scope, I don't see any of this sort of noise coming out. This is another type of positive fall exponent, negative fall exponent, positive logarithm, negative logarithm, positive fall logarithm, negative fall logarithm. This is a positive full wave, so that's sort of rectified. And I don't think I can lower that at all. This is a negative full wave. Let's change the volts here so we can see the full wave there. I'll go back to the positive full wave. Half waves. This is called a Lorentz on the function generator. This is a multitone, random noise, ECG, trapezoid, what's called a sync pulse, an impulse, and then a variety of other signals. So the function generator can generate all kinds of signals here. We can see, just go back to the sine wave. It'll take a minute. So works great for a sine wave. With the square waves and a lot of other signals that have discontinuities in their form, you tend to see this kind of pulsing at some of the edges, which is a sampling issue. A few features to have a look at in the oscilloscope mode that are really not well described. So if we turn the meter on, now I've got it hooked up to a function generator right now, and the function generator is outputting a 5 kilohertz sine wave. And so you can see that on the screen that doesn't look all that great because of course the ranging is not set up to really visualize that wave. It turns out that pressing this R button will kind of turn it off for a second. It does a little bit of analysis and it presents sort of an optimized display. So now we see what looks like a really nice sine wave, and the readout down here is showing that it's 5 kilohertz. Let's see if we can turn the brightness up there a little bit. So I'm hoping that you can see that this shows that it's seeing a 5 kilohertz wave. Now I can adjust the sine wave a little bit. So I'm going to increase the frequency of the sine wave. So now that's 15 kilohertz. That's 25 kilohertz. And you can see the meter has figured out that it's 25 kilohertz, but it's very compressed. If I press the R button again, it'll do some analysis. And once again, it comes up with a nice optimized display. And it'll do that even if I, that's a square wave. And so we'll go into this sort of ramp, and we'll take the ramp up to, or down. So that's now a 5 kilohertz ramp. And once again, I can press the R. It'll do a little bit of analysis. And so it provides an optimized display there. And it's interesting that the documentation really doesn't talk very much about that, but that's a very useful function to have. And hopefully I've saved you a little bit of time and trouble by pointing that out. Now, the oscilloscope mode also has a waveform storage mode, and that has a little bit of an odd operation. But right now it's showing a waveform here. And if I want to store this waveform, the first thing I need to do is I press this S key, and watch up here where it says trigger. Okay, it says stop. So now it's kind of frozen that waveform on the display, that's not stored yet. To store that, I take this S key and I hold it down for a couple of seconds. And that goes into this storage mode. Now this is showing me an empty slot. It calls them a record. So this is record 5. And if I want to save it, I press F4. And so that waveform is, and the different metrics that it took of that waveform are stored here in this record 5. And there are 10 of these slots for saving waveforms. And if I press F1, you can see I've saved a few different waveforms here in the different slots, and the ones that are not used are empty. So that's pretty clear. So those are a couple of nice features, because if you're out in the field and you're working and you want to kind of take a snapshot, you can do that. You just have to kind of be careful with the operation, because to get out of this mode as well, you press the S key for 2 seconds. Now it's still in this stop mode. I need to press S to get out of the stop mode. If you're not in the stop mode and you try to get into the saving screen, it gets a little bit mixed up. So just make sure that you're familiar with how that mode works if you do get this meter and you're trying to make use of it. It can be a little finicky in that regard. So those are two very nice features. I wasn't originally aware of this sort of auto ranging feature in the oscilloscope mode. And that's very good is when you take into account that by default, when it turns on, it always comes on in the default mode with a default range. And so just pressing that momentarily, it kind of pauses the signal, does some sort of sensing and analysis on the signal, and comes up with an optimized display. So that's very, very nice, very handy. Overall, it's nice to have a multimeter that can also do double duty as an oscilloscope. So that's a pretty nice feature. It's just not equivalent to an oscilloscope. I mean, it's about, it's a fraction of the price of a typical bench oscilloscope. And so for quick and dirty assessment of a signal to tell if a certain signal is roughly what you're expecting, certainly this will do the job, fairly inexpensive. But if you're looking for something that is very sharp, very precise, very accurate, this really isn't the solution that you would look for. And one of the other things that can be a little irritating with this, so you'll see that right now this is set up with 10 microseconds per division and 2 volts per division. That's sort of up here. If I turn that off and turn it back on again, it's back to some sort of default settings. Now let's have a little bit of a look inside to see what components are used in the construction of this unit. So here's an overview of the whole unit, and we can see here the plugs that are used for the test leads, various plugs. Now I'm going to zoom in a little bit just so that we can get a little bit of a better view of the different components. We're going to start here at the bottom. So let me just zoom in there. Okay. So a couple of things to notice. The fuses, if you ever have to replace them, would be a challenge to replace. There's one fuse right down here. That's one. And the other fuse is right here. And so I think one is a 10 amp fuse and one is a 1 amp fuse. I think that's the 10 amp. So that would be, they're all soldered onto the board. So that would be a challenge to replace, a little painful. A couple of other things to notice here. There are no MOVs on the unit, and so surge could wreak havoc with the unit. Now coming a little bit over here, we can see the sort of the maker of the PCB anyways. So it's E1 and the model is ET828 So we can try to look that up. I've managed to find some information on an ET828, which is an early version of a multimeter oscilloscope unit. The E1201C goes back to sort of 2017, so it's an older version. So this is probably a newer iteration of that. But I haven't seen, or I haven't been able to find any E1 branded units of this particular style. All right, now moving over a little more, there's this chip. The identifying marks have been removed from this chip, so I can't tell you what that is. A couple of other things to notice. So the main unit here, this is an ARM STM32F4, so that's a Cortex, ARM Cortex microcontroller. So a fairly powerful microcontroller here in the unit. And then this over here is an MS9280 analog to digital converter. And so I imagine that's used to convert the signals coming in primarily for the oscilloscope into more discrete levels in order for it to be able to display and sense that. Now we have, there turns out that there are two EEPROMs here. So there's one EEPROM here. Another way of saying that is flash memory. There's one here. And I'll throw the model number of the EEPROM for this up on the overlay. I think this is the one that's 256K. And there's another one which is EEPROM, which is a little smaller. That's this one over here. So that's also another EEPROM. And so probably different configurations. This could also be one of those sort of full DMM chips. So all the other multimeter functionality could be coming here from this chip. And this EEPROM might be intended to control the configuration of this multimeter chip. So there are a few of those multimeter chips on the market. And that's more or less it in terms of the major features to take note of on the board. There are a couple of test points here that are labeled RX and TX right there. Those are probably to allow for some sort of troubleshooting or assessment of what's going on within the microcontroller. I haven't tried that out, but somebody who's a little more adventurous than me might have a go with that. Those are all really the highlights on the board here. So in summary, looking at this unit overall, it's got all of the basic multimeter functions that you'd expect to see. So, voltage, current, resistance, diode check, all those sorts of basic features are there. Some of the things that are a little more common these days in multimeters, like non-contact voltage and hot wire detection, those aren't there. But then again, that's probably not the reason why you're getting a meter like this. You're probably getting a meter like this because of the graphical oscilloscope feature, and you're probably not all that keen on non-contact voltage and hot wire detection that are really sort of more esoteric features, if anything else. Now, the oscilloscope features, as I've kind of remarked earlier, it's really fantastic to be able to have this oscilloscope capability in something that is this portable, because that means that if you're out in the field somewhere and you're needing to troubleshoot and you say to yourself, wow, I really wish I had an oscilloscope with me to troubleshoot that. Well, now you can. You can have something like this, and the oscilloscope really, it works really nicely. There is a little bit of jitter, if you will, some sensing noise that I pointed out a few times. But in terms of being able to understand the shape of a waveform and being able to see the signal you're dealing with, it really works fairly well. The ability to automatically kind of come up with an optimized display with the R button is very nice. The ability to store a waveform for maybe some sort of future assessment after you've left the work site is really handy. So the oscilloscope features are what really put this meter into a totally different league. The multimeter functions, nothing wrong with them. They're reasonably accurate as well. This meter is something you'd want to look at if you're looking for something with really solid multimeter functions, along with a very nice oscilloscope capability. in a very nice, small, portable package. Okay, well, thanks for watching. I hope you found this video to be helpful. Please subscribe to my channel, and until next time.